The main idea of Claw is to take toxic land and use the power of plants to take the poisonous metals out of the ground, but then recover them using some very clever synthetic biology and other natural processes, so as we can produce metallic nanoparticles, which have lots of industrial applications, but also other really valuable byproducts that could be used for things like fuels, paints, plastics, or even pharmaceuticals.
The Claw project is into the circular economy, and what that means is we take waste and feed it back into the economy as a raw material. We at Claw are specifically doing, we're looking at contaminated land that's been used previously for mining or for industry and is contaminated by heavy metals. Taking the waste from the past, converting it into useful materials for the present and for the future.
The Claw project, we think, is unique because it brings together a really diverse set of disciplines and skills.
Our lab's role is identifying and growing hyperaccumulating plants.
What you're looking at is the pre-processing of the biomass as it comes in. What we want is to convert the biomass rapidly to a form that we can then take forward without all the resources being used up by the fungus growing itself. So this actually shows you some bacteria which now contain some of the key enzymes that are present in the fungi.
Here we have various types of biomass. Now we want to degrade it. You can either do it a very simple way, just composting with chicken manure, or you can use fungi, Phanerochaeta. I'm personally interested in working with thermophilic bacteria. Because it's thermophilic, it works at high temperatures, and that means when you develop a scaled-up process, you will have less problems with contamination. Obviously, when you degrade biomass, look, it's more dense, and the color is deeper, it's darker. Apparently, there's more stuff in here.
There's a need of developing new renewable energies. To do that, we need a reliable source of biomass. Biomass grow on the contaminated land can be a good option to source that biomass to produce for production of fuel.
With gasification, we exclude the air, we heat up the material, and that gives off a flammable gas, and it leaves an ash or a tar behind. And depending on the temperature we heat the material up to, we will get the metal driven off either in the gas or left in the ash or the tar.
With regards to being able to produce nanoparticles from the phytoremediation waste, we're using bacteria to do this.
When we grew our E. coli, our modified E. coli on the stuff that Newcastle sent were, it turned the arsenic into these fibres.
Bacteria that we thought would be able to bioremediate these contaminated samples, and we found one bacteria in particular was very good at doing this, and that's called the sulfur vibrio.
Okay, so to characterise the nanoparticles composition, we use this machine here. So one of the main uses of palladium nanoparticles in the future will be for fuel cells.
What we do here is we're trying to develop an efficient, what we would call an intensified chemical or biological process to convert biomass into higher added value products. As chemical engineers, we're very much focused on creating a proper process that can be commercialized. Having a load of arsenic contaminated land, that could be a good thing. You could have an arsenic rush rather than a gold rush, that kind of thing. If we could crack those problems and if we can create a market for these products.
And for us, we're really pushing the boundaries of the science, being able to create new nanoparticles, possibly novel functions in the nanoparticles. I think using biology, we actually might have access to nanoparticles which man can't currently fabricate, but the biology might be able to do it for us.